Okay, continuing with the topic of temperature and heat. Pot of water, another pot of water. Which of these is going to boil sooner? You put them both on the same hot stove. The one on the left, right? So from personal experience, if you want to cook pasta, what do you want to do? You put just as much water as is needed to cover the pasta, right? Like if you need that, you know that you have so much pasta, you don't want to like take a huge container with a huge amount of water. It'd take forever. And obviously the reason for that is for a given quantity of heat that you're putting into the pot from the stove, the less the water, the higher the temperature that the water reaches for that same amount of heat. So example, supposing I had $1,000 in my wallet, which I don't, right? So if you're planning on killing me after the class, it's not worth it. So supposing I had $1,000 in my wallet, if I were to divide it up, let's say we had 100 students in the class, right? So that's the amount of energy that I have available. So I give it to the class. If there are 100 students in the class, how much money does each student get? $10, right? So it's like the temperature of all of the students went up by 10 degrees centigrade. On the other hand, if I were to take the entire $1,000 and what's your name?
Me?
Yes. Jeremy. Brown? Jeremy B. No. Oh, I'm thinking of somebody else. Okay, sorry. So anyway, Jeremy. So if I were to give the entire $1,000 to Jeremy, right? What happens to his temperature? It goes up by 1,000 degrees in this analogy, right? So the same thing. If I'm putting in 1,000 units of heat into this pot and there are fewer molecules, the individual molecules get to a higher temperature compared to, in this case, where there are way more molecules, their individual temperatures don't get up as high. Okay, introducing the concept of specific heat capacity. The specific heat capacity is the amount of heat per unit mass that's required to raise the temperature of the substance by 1 degree centigrade or 1 degree Celsius. So if I put a certain amount of heat into the object and if its temperature goes up by 1 degree centigrade, so it's kind of like how much does it take to get you like highly excited, right? If you're a third grader, if I gave you like 2 candy bars, you get like highly excited. The older you get, it takes a bit more than the 2 candy bars, right, to get you as excited. So at your age, it probably take, what would it take to get you as excited as it would have if I were to give you a couple of Snickers bars?
$1,000.
$1,000? Okay, since you're on that. Okay, yes. Right? So now if I were in the habit of every time I wanted to get you kind of enthusiastic, give you $1,000, at some stage, what happens? $1,000 doesn't make it anymore, right? You'd be expecting 2,000 a pop, something of the sort, right? So let's say that your parents have been in the habit of giving you $1,000 every time you do something, every time you finish your homework, right? On the other hand, let's say Jenna's parents, this is when your kids growing up, right, were in the habit of giving you what? $100, $10 every time you did a good job, every time you got an A in your class, right? So as a kid, you get an A, you get $100 in a course. On the other hand, your parents gave you $1,000 every time you got an A, right? Now, if I wanted to, so there's some kind of conditioning going on there. So if I wanted to get a certain level of like interest or excitement out of you and a certain level of interest and excitement out of you, in your case, I can give you $100 and get you to a certain level of excitement and interest. In your case, I would have to give you 1,000 to get you the same level of interest or excitement, right? So it's like your specific heat capacity now is 100 and your specific heat capacity is 1,000, right? So in order to raise your temperature, let's say in this analogy, by 1 degree centigrade, I have to give you 100 units of energy. On the other hand, to get you to get excited by 1 degree centigrade, I have to give you 1,000 units of energy, right? Truth of the matter is then it's worth my while to get you all interested compared to you, right? If I had $1,000, I can raise the temperature by 10 degrees, whereas you can just 1 degree. What's the point, right? So that is an example, right? A difference in specific heat capacity. Think of Warren Buffett. Now, like you said that you would get excited if I were to give you $1,000, right? Do you think $1,000 means anything to Warren Buffett? No, nothing at all, right? On the other hand, like if I was teaching first graders, right, even $1 would mean a lot to them. $1 probably means nothing to you, right? If I had dropped a dollar bill on the floor, I bet most of you wouldn't even bother to pick it up. It's worth nothing. Okay, maybe that's pushing it, right? Okay, so specific heat capacity is the amount of heat per unit mass required to raise the temperature of the substance by 1 degree centigrade or Celsius. So we've all had this experience, right? Slice of apple pie, put it in the microwave, heat it up. You pick it up out of the microwave, the crust seems warm. Bite into it, what happens? You burn your mouth. So for the same amount of heat, effectively, to a first approximation, put into the pie, what happened was that the insides of the pie, the filling got much hotter than the crust. That's why we got full. We pick the crust up, it just seems warm, bite into it, you get burned, right? So what's happening is the specific heat capacity of this filling is lower than that of the crust. So for a certain amount of heat going in, the inside gets hotter, even more so than the crust that has a, think of the example that I provided, right? So the inside, the filling is getting much more excited compared to the crust that is not as blah. I have all my $1,000. I don't need any more.
You have to do the H2O.
Good point. Extra credit. Beyond the scope of this illustration, but you're right. The way microwave works have to do with a resonance, if you will, between the frequency. Microwave is just an oscillating electromagnetic field. Right? It's oscillating at a certain frequency. Turns out the water molecules, they are able to oscillate at that frequency. So it's kind of resonating with that. So what happens is, the way food heats up in a microwave is the water molecules in the microwave, they start, let's say the electric field is pointing in this direction, the water dipoles, if you will, try to line up in this direction. Then the microwave electric field switches to the opposite direction, the water molecules try to switch to the opposite direction. Right? So as the water molecules move back and forth, and they're in resonance, if you will, right? They're kind of linked to the oscillating electromagnetic field of the microwave. The water molecules then heat up, and they heat up the surrounding food. So in general, food that has more water in it is more likely to heat up more than stuff that's dry, and so on. Okay, same concept here. So we said for a certain amount of heat coming in that the filling got much hotter than the crust. Similarly, land versus ocean, right? Have you noticed that when you go to the Phoenix Harbor in the in the early evening, right? It's kind of cooler by the ocean compared to when you're like deeper inland, right? How many of you have noticed that? 3. Extra credit to those of you who have noticed it, right? So you've been paying attention. 5 of you have been paying attention when you go to the Phoenix Harbor, right? Now, this is one of the reasons why. Yes, mademoiselle?
It also happens when you're like in the park area.
Okay.
Park.
Oh, good point. Yes. If you happen to be near a park, right, like with lots of greenery, it tends to be cooler, right? Or if you're going on a walk in the evening, sometimes you'll notice that people who have lawns, you can actually feel a difference in temperature. Now, that's to a first approximation, right? Mm-hmm. There's another factor that comes in as well. The fact that, which we'll see probably in a later lecture, or we may already have seen, is the presence of moisture in the lawns. As it evaporates, it absorbs heat. It cools the surrounding areas, right? So there are 2 physics factors that are going into that. But good point, extra credit to you, right? So what is happening inland? So one of the reasons why people try to escape to California on a weekend in the summer, right, away from the Phoenix area, is basically because the areas near the ocean tend to be cooler. What's happening? What's happening is water has a high specific heat capacity. So the ocean, for a certain amount of heat coming from the sun, right, this has a low heat capacity, which means it gets more excited, it gets hotter. For a certain amount of heat coming in, the land gets hotter, so 25 degrees centigrade here. The water has a low specific heat capacity, so it doesn't get as, it has a high specific heat capacity, so it doesn't get as hot for a certain amount of heat coming in. So the water stays cooler in the summer. Now, in the evenings and so forth, like when you have a breeze that's coming off of the ocean, the breeze over the water is cool, and it feels cooler over here compared to deeper inland where we don't have the cooling effect of the ocean, and so the temperature is much hotter, right? So this is something that you probably all experienced when you're on vacation and so forth. Introducing the concept of thermal expansion, right? If we were to take all of you, I don't know if we can fit all of you into a Volkswagen Beetle, right? But we may be able to fit all of you, if you're like really scrunched together, into a telephone booth, do you think? I have no idea how many people you can fit in a telephone booth. But my guess would be that if we were to take a square, an area that's all of you standing like really squished, could probably, do you think you could all stand on this table? I'm not going to ask you to do it.
No.
Okay, how about 2 tables? If you pull 2 of these tables together, right? Now, if you and then what we do is we ask you to squish yourself as much as possible and as tight together as possible, and we reduce the volume that you're standing in, right? That is like a solid. Now, as the temperature goes up, you start wiggling and sticking your elbows out. What happens to the people next to you? Right? They try to move away from you, right? To give you room for your elbows. So as they move away, what happens is the solid expands. The minimum volume that you're occupying expands, right? It becomes bigger, which is what happens with metal. Any material. As the temperature goes up, what happens is the molecules and the atoms start vibrating. So they push the other atoms and molecules away from each other. So as they push each other apart, the entire object becomes bigger. So here is an example where it was, maybe New Jersey? Yes, in New Jersey. I forget what year. The temperature went so high that the trains, you've probably seen train tracks, right? If you look at the track, there's this metal track, then there's a gap, then the next line of rail, then a gap, and then there are wooden things that hold them together, right? So the reason for the gap is, as this expands, there's room for it to expand when the temperature goes up. If the temperature goes up more than you expect, then what happens is the gap between the rails can get completely filled in as they expand. Once they get filled in, then any more expansion of the object creates so much stress that you could end up with this, right? So what happens is you have to rip off all of these tracks and replace them. See the squiggle in the tracks? Because the railway lines, the metal tracks, had expanded sufficiently so they were now in contact with each other. When they try to expand any more, they go, and we miss you?
And when it got colder,
they wouldn't come back to the same. Yeah, they would contract, but this is permanent deformation. In elastic deformation, it'll come back to the same. But in permanent deformation, it doesn't know what way to go. So it doesn't come back to the same shape, right? So also this is the reason why if you look at bridges, even in the Phoenix area or a flyover and stuff like that, you will see there are these big concrete blocks or asphalt blocks. Then there is a gap, then the next concrete or asphalt block. And in the gap, over the gap, you have these metal interpenetrating fingers, right? So metal fingers like this with a gap. And the reason for this is so that when this block expands compared to this block, they can move towards each other. And there's still a gap that's covered over by these metal fingers that you can drive over, right? So if you were to build roads, every now and then you will see this even with pavements, sidewalks. Like when the temperature goes too high, you can see that the sidewalk buckles up, right? There's another reason for that too, and it's tree roots. Okay, so we've talked about thermal expansion. Now we can apply this in a technological application. Okay, there's basic science, applied science, and technology, right? Are you familiar with the difference? Nope. Okay, basic science investigates something very fundamental to the universe and it comes up with the laws, like the laws of gravity, right? Applied science says, how can we take that law and apply it in some fashion, right? Can we make something out of it? Technology is where, with that making something of it, we put it into a product that you can then sell to a customer and make money off of it, right? Ultimately, technology is the driving force for both basic science as well as applied science. If we did not have companies that create a product that to sell to the customer, that make a profit from it, we would not have the money to do either basic science or applied science, right? So basic is a fundamental understanding of the universe. Applied is taking that and trying to apply it to make something. Technology is to try to make something that's useful to a customer and selling it to the customer, right? And engineering is basically part of the, how do you take, it's the process of both taking things and making them into useful gadgets to sell, like DVRs or VCRs and stuff like that, and also the engineering of processes. And it's a bit of a circular argument, definition, but the engineering of the processes needed to do this. Okay, so here's a technological application. Something called a bimetallic strip. A bimetallic strip is a bimetallic strip because it's bi, it has two metals, metallic strip, right? So it's two strips of metal that are attached to each other. So here we have iron, if you will, that's bonded onto brass, or brass bonded onto iron. Now what happens is each of those has a different thermal expansion coefficient. At room temperature, they're both flat. Now I put ice on top, it cools the brass, and the brass contracts a certain amount. It contracts more than the iron does. So the top of the structure is contracting more, the bottom is less contracted. So what happens is this creates a stress that causes it to curve upwards. So you can see this kind of curve, right? Now you take the same object and you heat it up. When you heat it up, the brass expands more than the iron does. So the brass is trying to be larger than the iron, but they're bonded together. So the brass curves outwards this way. So you can see that in this case, the curvature is upward. In that case, the curvature is downward. Depending on your definition of upward and downward there. So here's a technological application. Very unlikely that this is an example of a thermostat in your house today. But thermostats used to be made like this. But what happens is you have the spiral bimetallic strip going like this to an oval cavity, and in this oval cavity you have a drop of mercury. When the temperature in the room goes up, it causes this strip to expand, to push outwards, and it pushes this drop of mercury up this oval cavity until the drop of mercury connects to these two wires. The mercury then creates an electrical connection between those two wires, which then switches on your AC. The air conditioner switches on, temperature drops. When the temperature drops, the bimetallic strip contracts, the mercury goes back down, there's no connection now between the wires, and the AC goes off. So the AC is off until the temperature goes up again, and the same process repeats, right? So this is an example of a technological application of the concept of thermal expansion using the applied science of a bimetallic strip. So this is a good example. See, this is a technological application, right? This is technology. That is applied science. The thermal expansion itself is basic science. Okay, you happen to be playing ping pong and you get a little over enthusiastic and you whack the ball, and what happens is the ball gets a big dent in it, right? So you have a choice. You can toss the ball, or allegedly, here's one way that you can repair the ball. Boil water, drop the dented ball into, as long as there isn't a hole in it, drop it into boiling water, and what happens is the ball heats up, the air inside the ball heats up, and it poof, oh, have you ever done that? Yeah. Okay, extra credit to you. So here's another possibility. Use a lighter, but not too close, because then you melt a hole in the plastic. You toss it? Well, in this case, see if it works. You can reuse it by popping it in there, and right? And it should repair the dent. And of course, take it out safely. Don't burn yourself and all that kind of stuff, right? Same principle where sometimes, like soda bottle, like if you cap it too tight, then and you put it in the fridge, then what happens is it'll get, right? It gets sucked in. So if you want to heat it up, then what do you? I just blow into it to blow it up. I mean, this is soda that just I'm going to drink, right? But
well, usually in Arizona, you just take it out of the fridge
and leave it out for a little bit, and it'll. Yes, you're right. Good point. Okay, so this is a description of the thermal expansion of water. Right? Here's the volume of water. Here's the temperature. At 0 degrees centigrade, water has a certain dimension, right? Certain, like ice has a certain size. As you heat it up, the ice actually melts and the water becomes more dense, which is the opposite of the vast majority of materials. Vast majority of materials, you heat them up, they expand. Ice, when it converts to water, contracts. Until at 4 degrees centigrade it is the most dense. Then you start heating it up further and it becomes less dense. Its volume increases. Until you reach 100 degrees centigrade, then it converts into steam and so on, right? Now this downward motion is actually critical for the survival of life on Earth. Okay, we'll see that in a future slide. But first we'll describe what's going on. Here's the volume of the water as a function of temperature. Here at 0 degrees centigrade you've got ice, right? So here's ice. It forms these 6-membered rings, kind of like a solid crystal. As you heat it up, it starts becoming water, right? So what happens is these bonds kind of let go of each other, and this empty space in between starts getting filled in with the water molecules. So the density, notice that the density of this, even though this is water, liquid, the density of this is higher, they're more packed in than in this case where the ice, the water is a solid ice. So the density goes up, which means its volume drops, and so we see the drop in volume. Then after you start heating it up past this point, you can see that the volume is increasing. Where these molecules start oscillating enough, they move apart. So that part would be this part of the curve as you start heating it up past that point. So you add the two of these curves together and you get this U-shaped curve. Now this U-shaped curve is critical for the survival of life on Earth. Yes, sir?
Wait, I'm trying to think. Because ice floats, even though it's more dense than like warm water.
Ice is less dense. Ice is floating because it is less dense. It's lighter than the water that's floating on, which is amazing. The solid is less dense. It's lighter than the liquid.
Okay, so at 4 degrees centigrade, the ice would sink. If you have ice in 4 degrees centigrade water, the ice is going to be at the bottom.
The ice at 4 degrees centigrade is not ice anymore. It's water.
If you have water that's 4 degrees centigrade and you drop an ice cube in it, will it sink or will it float because there's still air in it?
The water is the most dense.
But it went down.
It has if you look at this plot, the volume of the water is decreasing, which means the density is going up. The density will do the opposite, the converse.
Oh, okay.
Right? Extra credit for the question. So, actually this is critical here. Let's say that we have minus 10 degrees centigrade, right? Up in the atmosphere and so forth above, right? I think of the Arctic, temperature minus 30, minus 40 degrees centigrade, and you've got open water. What happens is the water at the top starts cooling down until it reaches 0 degrees centigrade, starts converting into ice. The ice is less dense, it's lighter than the water, so it floats to the top. Now, the water starts cooling down, 0 degrees centigrade, but on the way to reach 0 degrees centigrade, it reaches 4 degrees centigrade, right? Say water at 50 degrees, cooling, gets to 4 degrees. It's the most dense. 4 degree water reaches the bottom. It's the most dense, so it sinks to the bottom. So as the water cools down, the coldest that this water is going to get is 4 degrees centigrade. What happens is the ice acts as an insulating layer that protects the rest of the water from the temperature above. This is why an Eskimo can be warm in an igloo. I used to wonder that about this as a kid. Make a house totally full of ice, right? With ice walls. How can I stay warm in it? You're comparatively warm when the walls are made of ice because the outside is like minus 40 degrees or minus 30 degrees centigrade, right? Of course, you still want to have fur and stuff like that, right? To protect you. Now, the fact that the water does not freeze all the way down because the ice is providing an insulating blanket is what makes it possible for life on Earth to survive ice ages. If it were not for this fact, if water didn't become more dense than ice, let's say that ice is heavier, like any normal material, take iron, whatever, you heat it up, the liquid is less dense than the solid, so the solid should sink to the bottom. If ice and water were to do the same thing, as you go through an ice age, what happens is the ice, as soon as it forms, it sinks to the bottom. So you get the bottom filled here, right? Then more ice forms, fills. Before you know it, the entire pond is frozen all the way up. What happens to all your fish? Right? What happens to all your whales, dolphins, you name it, right? What happens to all your plants? Now, a good case can be made for the fact that if you were to freeze all of the life in the oceans, you'd basically wipe out the entire biocycle and you would destroy all of life on Earth. Right? So, the first time you have an ice age, if you didn't have this property of water, you would wipe out all of life, except maybe some bacteria.
They have the funnels that come up and shoot the really hot water, and there's
then you
crabs.
freeze that too. You freeze the crabs.
Oh, so okay.
You'll have like totally frozen crab.
So you stop the heating of the earth coming out of the thermal.
Yeah, well, so even if you had a tiny little ecosphere right just there where the heat is coming up.
Life, there would still be life. Right
yes,
there.
but then you'll run out of nutrients and things like that, and they'll all kill themselves off. I think a good case.
They would eat each other. So they have each other's own little ecosystem and feed off of stuff.
And then as the temperature gets deeper and deeper, that'll encroach even further and further, and the room that you're living in will get smaller and smaller and smaller. Yes. Okay, let's move on. Extra credit to you, right? Okay, that was chapter 15. We shall move on then to chapter 16.